Okay, thank you everyone for coming this evening, and thanks for the opportunity to allow me to give this lecture called Reflections on Some Human Dimensions of Coastal Zone Nutrient Fluxes. I have two aims, primary aims for the talk. Revisiting an old idea that's useful to think about the impacts to the coastal zone, and a newer idea, but one that's still been around for 15 years or so. These two approaches that I'm going to be discussing represent different conceptual frameworks or approaches. The first of which has been used primarily to look at change over time, and the second one primarily so far to look at spatial changes, but you could use either one to look at both spatial or temporal changes. The first method that I refer to, the approach, is a classic now, Ehrlich and Holdren's iPad equation. For those of you who aren't familiar with it, it gets its name from its form. I equals P times A times T. I meaning generic environmental impact. P is population, human population, number of people. A is a measure of affluence, typically measured as the GDP, the gross domestic product of a region, in terms of value per capita, or production per capita, dollars per person. And T is some technology factor, which is usually measured as the amount of some technological procedure or some technology which can be delivered that will affect the environment, but it's measured in effort per unit cost. This equation grew out of a debate between Paul Ehrlich, John Holdren, and Barry Commoner in 1970. And Barry Commoner was a scientist who was concerned primarily about technological impacts on the environment following World War II, such as the development of detergents and pesticides, things like that, fertilizers, and had written some things that essentially blamed technology for a lot of environmental problems. Ehrlich and Holdren took the point of view that even if you had the best management of technology in a world with too many people or people consuming too many resources, you would still have problems. And so they were emphasizing the P and the A, the population and the affluence of the population. So this formula, very simple, describes how our growing population, affluence, and technology contribute to problems. I'm going to take you through some of these factors, all three of the factors, and just give examples. The first one, population. In this case, I'm showing the change in population over the last 200 years or so. For the globe, in dark blue. China in red, the European countries, 30 of them are in green, and the US is in lighter blue. And on this scale, it's pretty clear that the world has been growing exponentially over that time frame, although perhaps not in the last, say, 10 to 20 years. It's still increasing steadily, and China is also increasing steadily. On an exponential, on a logarithmic scale, it's much clearer. Linear trends on this kind of a plot indicate exponential growth, and it's clear that the world, China, at least over the last 50 years or so, Europe over the last 200 years, and the US over this period or so they've all been growing exponentially, but perhaps at different rates. So clearly population is growing at an ever-increasing rate. Affluence, here measured as GDP per capita and corrected for inflation, so that we don't have to worry about the change in value over time, shows similar increases in growth. Here's the US. Over the last 50 years it looks pretty linear, but over the whole period it's exponential. Europe, steady increase in growth over the last 50 years or so. The globe, steady increase over those 50 years. China, clearly, especially in the last 20 years or so, has been growing exponentially in terms of affluence. Not too surprising. It's also evident that given that this is the global increase and that we have a few cases of nations growing at a much, in terms of their affluence, at a much higher rate than the global average, there must be several nations and regions down here well below the global average too. So clearly there's a lot of regional variation in this affluence measure, which again is no surprise to anyone. Here's an example of a technology factor. In this case, I plotted the amount of ammonium fertilizer that a farmer in the United States can purchase per dollar, for a given dollar, and the units are kilograms per dollar. And what this tells us is that over the last 50 years or so, at least in the US, the amount of fertilizer, the trend in the amount of fertilizer that you can buy for a dollar has been going up. Again, this is corrected for inflation. Although there are clearly significant deviations, and if you look at the time here, they're probably related to the price of energy, because ammonium nitrate fertilizer production is very sensitive to the energy consumption. So, whereas technology could be counteracting the effect of population and affluence, in this particular example, it's actually exacerbating the problem, because farmers have more fertilizer available to them, and as a result they waste more fertilizer than they did today than they did in 1950. Even in considering this recent downward trend, at the end of the period, the amount of fertilizer you can buy for a dollar is still higher today than it was in 1960. Consequences. Well, population is apparently growing exponentially. Affluence per capita, even, so far is increasing steadily, maybe not exponentially anymore, although there is significant variation regionally. Technology may be increasing or decreasing depending upon what's being evaluated. I just showed fertilizer price, or the inverse of fertilizer price, but there could be other technologies which actually counter this trend, and so it's much harder to say. Consequences. It's clear that in the Anthropocene, impacts are due to anthropogenic sources. That's obvious. Impacts, that is pollution or nutrient loads in rivers, for example, are related to the numbers of people around and the amount of stuff that they have. And it's clear that in order to maintain a fixed level of impact, that is, if we wanted this impact to stay constant, forget about it decreasing, we would have to have a corresponding decreasing effect due to technology to counteract the observed increasing effects of population and affluence. Given the example of fertilizer that I just gave, this doesn't seem very likely, and for most technologies I think it's an unsustainable proposition, which reminded me of, if you've ever read Lewis Carroll's Through the Looking Glass, there's a famous scene in there in which the Red Queen is saying it takes all the running you can do just to keep in the same place, and that seems to be true today. Just to demonstrate that, in fact, there are consequences, that this does translate into an impact, this is some model estimates of riverine nitrogen fluxes that Pam Green et al. Published in 2004. The top slide is estimates of pre-industrial nitrogen flux at various river mouths around the world. You don't really need to focus on that one, but the bottom one is the main one. It's the percent change estimated in total nitrogen river flux today compared to this pre-industrial state. And the big picture is most of the rivers show up in black, which indicate a greater than 80% change. That to me seems somewhat conservative, but still it indicates that we've effectively doubled the amount of nitrogen coming out of rivers from pre-industrial days, at least according to this estimate. Similarly, if you look at atmospheric deposition, this is a study by Jim Galloway and others from 2004, comparing the estimated nitrogen deposition globally in 1860 compared to today, or rather the early 90s. And it's pretty evident that, especially in the developed parts of the world, nitrogen deposition has increased enormously compared to what it was in the mid-1800s for two fairly obvious reasons. One is the development of the internal combustion engine, which is a primary source of emissions of atmospheric nitrogen, and the other is probably the development of the Haber-Bosch process in the early 1900s, which is the procedure by which nitrogen fertilizer is synthesized, which can lead to volatile losses of nitrogen to the atmosphere. So there's clearly an impact on nitrogen globally. Switching gears a little bit from IPAT, I'll talk a little bit now about something that I spend a lot of my time on, watershed nutrient accounting. And this is the methodology that, at least so far, we've used to look at spatial variation across watersheds in nitrogen fluxes. It was, to the best of my knowledge, it was developed at a workshop on Block Island, which ultimately was published in this book on a special issue of Biogeochemistry in the 90s. The primary aim was to show the relative importance of various nutrient inputs to watersheds and their effects on riverine fluxes to coastal waters. And I'll just take you through this very quickly. It's essentially a mass balance technique. You have inputs to watersheds. This applies to any nutrient, not just nitrogen. Outputs from watersheds, and the difference is due to some sort of process which consumes or produces nitrogen within the watershed. And for those of you familiar with the Loicz coastal waters biogeochemical budgets approach, it's very similar in principle to that. For the case of nitrogen, what are the inputs? Fertilizer is a big one. Food and feed import to a watershed, that is the nitrogen in foods and animal feeds coming into a watershed. Atmospheric deposition of nitrogen. Nitrogen fixation due to crops like soybeans and alfalfa and things like that, which fix gaseous nitrogen and turn it into forms of reactive nitrogen that plants can use. On the output side, you have riverine nitrogen fluxes and also any food and feed export that's leaving the watershed, being produced in the watershed but leaving. And on the internal processing side, which we call watershed retention, you have denitrification, which essentially is gaseous losses due to microbial processes within the watershed, turning nitrogen into nitrate gas, which effectively disappears from the watershed. and then storage of groundwater in groundwater, things like that. So fairly simple methodologically. We're doing a mass balance, assuming steady state inputs minus outputs, inputs minus outputs minus retention equals 0, a mass balance. And we're often using, measuring these things in order to estimate the retention.